I'm not sure if you can.
It says it's recording.
It says it's recording, yeah.
Okay, cool.
But I'm not sure if it's true.
Oops. All right. Well, we're going to go ahead and get started now. Hello, everyone. I'm Trip Collins, and on behalf of the WISE group, the WISE Zoominar committee, I'd like to welcome you to the January 2026 edition of the WISE Zoominar series. So, Happy New Year. Today's theme is wave spectra and currents from Nadir Imagery, and in this case, I think we're talking about making measurements from uncrewed aerial systems or drones. And first up, we have Micheal Stesser, who is currently a postdoctoral researcher at the Institute of Coastal Ocean Dynamics at Helmholtz-Zentrum Hereon in Germany. And Micheal, the floor is yours. Go ahead.
Yeah, thanks, Trip. Thanks for the invitation and for the chance to speak. I think I still have to load my stuff here that you can see presentation. Can you give me a go if it's
Looking good.
there? Okay. Yeah, so I'm going to be talking about current retrieval from drone video, actually. It will be about a tool that we developed called CopterCurrents, which is a team effort. So I want to acknowledge the work and give some credit to my co-authors. Jochen is the department head of the Department of Radar Hydrography, and he was pushing the idea from the very early days forward. And Ruben deserves a lot of credit for most of the writing, I would say, of the code and processing stuff, at least in the early, in the later stages of the developments that we did. Yeah, radar hydrography. I mean, uh, why radar if the talk is about drones? Here's a bit of the stuff that we do with radar. We are developing our own marine radar system that is coherent on receive, and we use it mainly to derive hydrographic parameters for it that are needed, of course, for various aspects in science. The coherent version, if you're interested more, it will not be part of this talk, but that helps a lot for retrieving sea state and wave breaking parameters from the radar data. This talk will be about currents, which was also from the beginning one of the main applications for marine radar retrieved stuff. Also nice to have is always surface features that we call it, what we can use nicely, for example, here to monitor sea ice or drifting macroalgae or internal waves of fronts. So this is our background. And you will see in the later parts that it's also partly related to the drone efforts we then made. So I compiled a little bit of a timeline. So CopterCurrents came out, I think, in 2019 when we made the code available. It's a MATLAB-based open source tool to derive currents from drone videos that we acquire mostly at Nadir. And it's based on linear wave theory. So as always, it takes a while until theory comes into application. And as I said, we have a long history at our center for marine radar-based wave and current retrieval, which is actually the same techniques and methods that we apply later for the drone stuff that ended up when it started in the 80s, ended up later in a spin-off company and Waymo's operational wave monitoring system that has gained some success, I guess, internationally. Some people may know it. If we're talking about video, then actually the story starts a little bit earlier, a few years, where people did it the first time from a platform with video data using 3D, like image sequences to derive currents. It has also already been done from airplanes on airborne data. So we are also not the first ones to do this. but we were the first ones to apply it, as far as I know, to drone data. And what has changed, I would say, in the recent years is that the technology has advanced a lot. So that makes it nowadays much easier to geocode the data which is needed for the processing we do, and also processing power itself has become much better, which helps us to overcome lots of the problems that the previous people had. A few words about the fundamental concept. I think in the WISE community here, I don't have to introduce this equation, which is the linear dispersion relationships for gravity waves, which I mean, if you have an underlying current, then you have a Doppler shift induced into the observed frequency. So intrinsic frequency is shifted. And if you plot this in the wave number frequency domain, which you see here on the right, then you have a certain region in your k omega spectrum where you see wave energy, and this is then either speeded up, shifted upwards, or slowed down, shifted downwards, if you have a current. So far, so good. I think this is known. This is something that is not so often seen, I guess, because normally you don't have 3D data from other sensors. So because waves are directional, of course, so k and u are vector quantities, have a direction. And then your dispersion relation, the equation before, appears as something that we call the dispersion shell in the 3D space. And this shell gets then shifted by the current, or tilted, I would say, if you have an underlying current, right? So this is the whole theory. We don't need more, actually. It's quite simple. But it works extremely well. I want to show this example as an example where we apply this on radar data. This has been acquired from Largemont Lighthouse that you see here with Jeff Philippot and colleagues, many others actually involved there who use this nice site for studying loads on structures. So if you don't know that work, I highly recommend this paper here. There will be a reference list in the end, so you can find it easily. And these current fields, the radar current fields that we get from these images that you see from on the left, they are super accurate. I mean, we found, like, Björn Lund in 2018 already published a paper where he validated these fields against drifter data extensively with an accuracy of down to 4 centimeters per second, which is amazing, I would say. Yeah, so, and now drones. So this is typically data that we get from the drone. And actually, when we first saw these kind of images from drones, we saw that, okay, this must work, right? So, I mean, if a radar image looks like this, we see these waves, then this kind of stable imagery that we get from the drone must work. And so it was. I want to point you a little bit on the different scales, right? With the radar, we see 6 by 6 kilometers. The radius is mostly like 3 kilometers wide. And we have the rotations give us the frame rate, right? So it takes normally two seconds to update the full picture. And with the drone, we have up to 60 frames per second, which is totally different. We have, depending on the flight height, of course, a different footprint, but we also have a very high resolution in space, right? And that makes the spectra that we get out of it a little bit different. So if this here is an example for a radar-derived spectrum, which is of course a 3D spectrum, right? So we do a 3D FFT on the image sequences, end up with this thing that you see here on the right, this cone-shaped dispersion relation. But then if you slice it here, and in the rest of the talk, I will only show these slices because it's much easier in 2D to show on slides, I guess. Then you see this on the left. And so the Nyquist frequency here is about 1.6 radian per second. And if you compare that to drone data, then your radar spectrum would cover this range, right? This is a drone spectrum that we get out of a drone with this example is with 25 frames per second. So we are extremely rich in data. And the first time when we tried, the first time we didn't know where to look because the wave, the region that we normally look at with radar data, there was nothing to see, right? So nowadays we cut this region because of course the shorter waves gives you much stronger Doppler shifted signal that you can easily identify. And we also reduce the data because it's so much to 10 hertz or something like that, which is still more than enough to do this. And a few words about how CopterCurrents then works. So this is the spectrum. So what we do is we define a certain filter width along the dispersion relation. And as I said, we are nowadays we don't have to be careful in terms of computing power anymore. So we simply brute force all possible currents that we define in a certain region, and we come up with these maps here. It's a visualization of the energy collected for an expected current, right? You see Ux on the x-axis here and Uy on the y-axis. And then you test all the different dispersion relations that are possible and you collect the maximum energy. If it looks nice, you come up with a clear peak, which we consider then as the most probable current. And that's all we do, right? We then do that in a moving window on data. This is an example, one of the first examples that we did at the Weir in Geesthacht, because it's in front of our workplace here. And this is the resulting current field. So since the water is flowing through the through the gates that are open here, we knew that the result cannot be so wrong. At that time, we were also afraid that people would not believe us that we can do science with these kind of toy drones, actually. But that changed very, very early, very shortly after, when we then designed a validation campaign, also at the Elbe River in Lauenburg, where we took some ADCP data for comparison. And this is then published in the CopterCurrents well, at that time it was not called like that, right? In the basic paper that I wrote in 2017, where we had this field. So this is a comparison then, or this is first the field of ADCP derived vectors. So far, so good. And this is what we get from the drone. If we go back and forth, then you see that it matches quite well. And if you compare in terms of error statistics, then you come up with 9 centimeters per second error, comparing these two data sources, knowing that we are not exactly measuring the same thing, right? The drone is measuring 30 seconds as a map, and the ADCP is going through the area to create the map. And of course, the river has some turbulent features, which will not appear then in the ADCP data. So we expect actually some variability in the measurement. So it's not a ground truth validation, but it's actually what we would do normally to acquire some data. So errors is good. And what's also amazing to say is that, of course, the ADCP survey took us about 2 hours, excluding, I mean, this was only to collect the data, excluding processing. And the drone video is 1 minute, or I'm not sure if we used 30 seconds or 1 minute. I think in the paper it was 1 minute data. But that's you can go down with the time. So that's a different. We then later on try to apply it whenever it's possible to help public institutions, I would say, in Germany. This is an example in collaboration with the Federal Agency for Hydraulic Engineering, where they were interested in the flow through this river storm surge barrier. This is then a construction of multiple of these images that you saw before, in a 15 minutes flight mission on the one side and on the other side, just as an example. Another example application was with people who were interested in the flow between river groins because they study the effect of the flow velocities on biology in the river. There we also did additional ASV, like automated surface vehicle measurements, equipped with an ADCP. And all these experiments were always showing us the same range of errors, I would say, below 10, way below 10 centimeters per second. It's mostly better. So we are quite happy about this outcome and this results. And a little bit more back to the scientific side, because this three examples that I showed in the slides before, they were all taken at pretty low wind speeds, I would say, almost no winds. Here in front of Miami, or in Miami, in front of it's the Bear Cut Inlet, in front of Rasmus, we were able to participate on an experiment that we did together with the Carthy Consortium. So thanks to these people for hosting us. There, the plan was to use these nice locations where you have tidally induced currents in and outgoing this Bear Cut Inlet through this bridge here, what you see. And we had pretty constant winds from the east. So we were using that to see how the data reacts in different situations. This is then these stitched maps. That's not geocoded, but this is where it belongs. You see that that there is a submerged shoal here where the current is kind of also or this induces some horizontal variability as well, which gave us a nice data set, and we had some drifters drifting through the data to see how's the outcome to make it a bit bigger. So this was then current with wind, where we see this comparison, so drifter velocity against drone velocity. And we can see that if wind is with the current, we have a slightly higher velocity measured by the drone, whereas for the opposite situation with currents against the wind, we have a negative bias, meaning that the drone measures a bit slower velocities. This is, of course, most likely related to the fact that the drifters were equipped with a sail, and the drone is actually measuring the very near surface upper centimeters current of the water column, and we try to investigate this a little bit more in detail by holding the drone still for a little bit longer, and dropping some like a range of drifting things that we consider to be connected to different depth in the water column. So we deployed oranges and bamboo plates in addition to the drifters, and let them drift here through a region where we had also comparison to ADCP data. And the preliminary result is that it gives something that that is targeted in the right direction. The oranges that you see here in this plot were drifting a little bit faster than the bamboo plates. And the dots that you see here are the drone-derived currents, by assuming different ranges of wave number, which connect to different depth, right? Because shorter waves are connecting to different to a higher region in the water column. And yeah, I mean, what we need to say here is that the signal to noise ratio for the upper 5 centimeters is pretty low, and you see also some outliers there. So, I mean, the trend is correct, and I think it nicely shows that it's also a tool that might be valuable for scientific studies. But I would like to say that there's still work to do. Say what goes in the right direction. This is the same slide that I showed before, so no need for further introduction. But what I want to draw your attention to is this region here where we actually don't have good data. If we So there are some holes in the data. So if we extract this kind of source video, I actually don't know if I picked exactly the right one, but I think it shows what I would like to visualize here. What you see here is a blocking point where you have current-induced braking happening. And this is a problem for copter currents, right? This is a limitation. If we have foam or braking waves or other drifting stuff, then the signal to noise ratio is reduced. The current estimate is not good anymore. But the good thing is that the SNR already tells you if your if your retrieved current is, if you can trust it or not. And yeah, so we basically always do automated filtering based on the signal to noise ratio, which works pretty reliably. We're also working on different methods. So the good thing is that if you don't see or if you have braking waves, then you mostly also have foam, and then this foam starts to drift. So in these situations, then you can use other tools to track the flow, like particle tracking, velocimetry, or PIV. Um, yeah, I mean that's basically already what I wanted to say. I think, or I hope that this presentation convinced you or showed you that copter currents can be used as a practical tool for surface current field retrievals from drones. It has one main limitation, I would say, that you need waves, but uh, I mean, you see waves in many situations. And as soon as you see them in the images, then you can be quite sure that copter currents will work. We have now validated it in different environments with always showing errors below 10 centimeters per second, which comes close to what you could expect for an ADCP. It automatically tells you if your data is reliable or not based on the signal to noise ratio. And it can measure currents in the upper few centimeters of the water column, which is making it a nice addition, I would say, to ADCP data. I mean, we don't claim that we want to replace traditional tools of measuring currents, right? It's complementary, and that's good. And it's easier, I would say. I mean, these drones are nowadays easy to fly, with the biggest problem for us sometimes acquiring permits. It's not about maneuvering them. Yeah, the code is open source. It's GPL licensed, so we are happy if people use it. We are also happy if people um, feedback some improvements to the code base. And we have a project page if you're interested. Honestly, I think it requires some update, but it's there. So yeah, feel free to check this out. And I promise this list of references here. And since this is recorded, I only have to leave it for a few seconds, I guess, here. And with that, I say thank you for listening. I think happy to take questions.
Excellent. Thank you so much. While we change over speakers, if anyone has a burning question, go ahead and jump in or put it in the chat. Otherwise, we'll have a little bit of time after the second speaker. We'll have a bit of an open floor then as well. Otherwise, I'll go
I
ahead
have a
and
really quick question.
go for it.
What drones have you used? Like what manufacturer?
Different ones, but I mean, we mostly entirely use the DJI drones. And we have good experience with them, and all of them basically. Some of them give you a little bit easier access to the telemetry data that you need, but that's also, yeah. I mean, you can also write it down if needed. It's of course easier if you have easy access to where the drone is and where it looks, because that you need for the georeferencing.
Micheal, would you go ahead and stop sharing your screen so we can get
Yeah, sure.
Yep.
Sorry.
All good.
I just have to find the button, which is here. Yeah.
There we go. Like I said, we'll have a little bit of time after the second talk for questions. So go ahead. If you have a question, go ahead and hold it till then. So next we have Aviv Solodak, who's a senior lecturer at the Freddie and Nadine Herman Institute of Earth Sciences at the Hebrew University of Jerusalem in Israel. And I'll let him go ahead and take the floor.
Thank you very much, Trip. Thanks for having me. Very glad to be here. So this is work done with my colleagues, Yaron Toledo and Vika Grigorieva from Tel Aviv University and Yoav Lehan from University of Haifa. And it's basically a continuation of Micheal's talk because basically it's an extension of the CopterCurrents package to estimate wave spectra. Now, I'm a physical oceanographer, but my background is not exactly a wave guy. So how did I get to that? So the same colleagues, Yoav and Yaron, were working on jellyfish swarms, and I was excited about using CopterCurrents for other stuff, sub-mesoscale and so on. And I talked to Yoav about that, and he's like, "Oh, come do it in." We have a lot of we studied them using the jellyfish using drones, and you can help us figure out what the velocities were. They were trying to see how it aggregates. This is the end product of their work. Long story short, they say, well, actually, it looks like the results don't correlate. The velocities don't correlate with the jellyfish motions. Maybe it's the waves. Can you get the waves? So we thought about it a bit, and eventually we did the work I'll present. But eventually, what we found in their work was that these are the jellyfish trajectories in a movie, and they go in a specific. First, they go in a specific direction. So from green to red, they're all sort of northwest here, and the swarm as a whole moves in this direction westwards. The current direction was this way. The wave direction was to the east, opposite. This is one movie, but there were multiple days, and it seems to correlate. And if you're interested in what we thought happened there, you can look at this paper. But anyway, let's get to the drones and waves. So Misha talked about this. Why use drones? The low cost, but also importantly, they're just available. Like in that particular project, they've been using them for a different optical reason. So a lot of people use them today for various reasons. So they're just available in research groups, universities, and so on. Deployment is easy. They're mobile. You can get synoptic data. This was all mentioned by Misha. So you can get a whole area, not a huge one, but a whole area at once. You can operate them from research vessels, from shorelines. Okay, so we see signatures of waves. You obviously see a wave moving here. Why is that? So basically, it's because the slope of the waves causes a reflection of skylight from different directions, and the skylight has a gradient in brightness. Normally, if it's not too cloudy and so on, it's brightest at the horizon. Another reason is Fresnel reflection depends on the angle, but in any case, it's modulated by the waves. That's why we see it. Skip this. Of course, there's some issues. Sanguine breaking waves, turbulence, that complicates all this. This is what I've just said, basically. So the wave at the surface causes a reflection to the camera specific pixel, which observes a certain direction from the drone, sees light coming back not from here if it was a flat surface, but from a different angle. So if the skylight is brighter here, for example, you'd see a modulation of the brightness. All right. So basically, the basic operation of CopterCurrents is to take Fourier transform in both spatial directions and in time, and you get a spectrum that's from the original paper of Micheal. And this is obviously a reduced spectrum here to 2 axes out of 3. You can look. this is from one movie that I analyzed. You can also just look at KX, KY spectrum, obviously. You can cut it any way you want. But this is not equivalent to the wave spectrum. Now, because it's a spectrum of gray levels of the brightness signature of the waves, not of the waves themselves. And I think this is just fine for the purpose of measuring currents because they just depend on the Doppler shift. And the Doppler shift per wave number will still cause, basically move the dispersion relation, that the highest brightness per wave number would still be at the right frequency for the optical spectrum as it would for the wave spectrum or side spectrum. So if you optimize your velocity as it does as it's done in CopterCurrents, if you optimize it to get the right velocity based on heating and dispersion relation, you should still be fine. The wave number should still be fine. But the spectrum that's used here is the brightness spectrum. So what we wanted is the wave spectrum. Okay, so I just said that basically. So we expect basically the frequency at which the spectrum to pick at the right k omega combinations, but for example, the ratio of the spectrum at one wave number and another wave number would not be the same as in the actual system's Helmholtz spectrum. Okay, so we found, or we suggested a semi-empirical way to sort of inverse this the brightness spectrum to the system's height spectrum, and basically it begins the same way, rectification, and then we also do the trending and windowing as is normally done if you're actually interested in the spectrum itself. And you run the FFT, you get your spectrum, right? We've looked at it before. It's another way to cut it. And then we do a few different things. One, we calculate some reference illumination. I'll explain what that is. And we use that eventually to derive the spectrum. So let's see how that works. So first, where's my cursor? Sorry, having some issues here. No, that's fine. So first, let's consider the brightness I at a certain angle of view. It can be a 2D angle of view from the camera, from the drone at some time. Then you can consider it as if the amplitudes of the waves are not too large. You can consider that it will be equal to just the brightness that you get from the same direction in the absence of waves, if the surface was completely flat, plus some deviation. So the first term is the flat surface, sort of hypothetical brightness, and then the deviation would be basically how the gradient of the illumination from that direction, which is actually the direction of the sky as well, because of the angle of incidence being equal to the angle of reflection. So it's basically how the brightness of the sky changes at a particular angle as you change the slope. So that's quick explanation of this equation, which is approximate. And then we also use the fact that a gradient relative to the slope is basically twice the gradient equal to the viewing angle, because as you change your I don't have a cartoon of this here, but as you change your surface angle, the reflection angle grows by a factor of 2. That's true in 2D geometry. In 3D, it's not quite true, but it's close if the slopes are not too large. And then if we just apply it, and in the first move this term to the left, use this, you get this equation, and then if you take the Fourier spectrum of that, and that's basically your video, take the first bit of the video minus this, and that's the reference illumination that we'll see how we estimate it in the following slide. So let's say we know the reference illumination, we subtract it, we take the Fourier spectrum, and we get the Fourier spectrum of that. Now, this is the Fourier spectrum of two factors, and the result should be convolution of the two spectra. But let's first assume that that this one is constant. What does that mean? That the skylight brightness gradient is constant. If we look at a small sub window of the full movie, full frame, then that might be a good approximation. Let's do that for now. And if that's the case, then you just take the Fourier spectrum of that, and the gradient is like k dot something in Fourier space. So that's what you get. Take the absolute value squared, you get the spectrum. So the spectrum of the optical spectrum of the movie minus the reference, that is equal to the spectrum to the absolute magnitude square of that. Now, and then we're going to call the direction between a wave number k and the brightness, the scalar brightness gradient direction. We're going to call the angle between them theta. So we get this expression here. Okay, so basically the skylight, the optical spectrum is equal to the elevation spectrum or wave spectrum times the brightness gradient of the sky squared times k squared for the same k times the cosine of the angle squared, the angle between k and the gradient of the brightness. Okay. Now just divide by this factor here, and you get the wave spectrum. Okay, so that's one thing. There's actually at least one issue with this, which we'll correct in the following in a few slides. But first, what is the actual reference brightness? So so to define it, first we do a few steps. It's basically, you know, if you can think of it if you have your movie and if you just average it over in time, so just average over all frames. In a way, it should get rid of the brightness modulation by the waves, right? So that's about what we do, but for more robustness, we do it slightly differently. So first we take a moving median in X and in Y. So that's scattered illumination shouldn't vary on small scales. So we take a moving median with 6-degree moving median to just remove some noise. Then we take the median in time instead of an average in time. That should get rid of the wave modulation of the brightness. So that should give us the end result, which is the reference brightness at every pixel or every direction of looking. But we also then do a Gaussian smoothing with 3 degrees standard deviation, and that just pre-smooths before we calculate gradients later, because we're talking about gray levels here, so it's integers. So to take the gradient, it's better to avoid jumps. It's better to smooth it a little bit. So that's how we define the reference brightness. And then because we assumed previously that we have this gradient is constant, the gradient of this quantity is constant. So let's find this constant, the best approximating constant or best approximating gradient of the brightness. So we just fit a plane to this. So this is a plane fit plus some deviation. The plane fit is a plane fit. So just be linear in the viewing angles, and we have some residual. Okay, so let's get back to 2 slides ago. We defined the spectrum, the wave spectrum from the optical spectrum this way. Now there's one problem with this is that there's a singularity here. So if for a certain k, the wave direction k is 90 degrees to the skylight gradient direction, then you're dividing by 0 here, which doesn't make a lot of sense. So that's an issue, obviously. And we suggested to resolve it this way. So this happens because we took a couple of approximations, but the main one was that we assume there's one specific direction, and the gradient is constant, the brightness gradient is constant. So we need to correct for that. So we basically do this semi-empirically by adding a term here. Specifically, we add this residual that I mentioned. So we take this residual and we now take the gradient So we have the gradient of the plane fit, and we take the gradient of residual, take its standard deviation over the entire window, and that's a value. Okay. So the idea is, if we didn't do this, if we would have been able to, we would have just done the calculation here, taken the full, convolution of this. And the idea is that, in my mind at least, that if the convolution of the nonlinear part, the residual part of the brightness, would be sort of just this noisy thing. So it would just be, it wouldn't have a lot of some directional coherent information, but just be some number if you, that would be a good approximation for it. So that's what we tried, and we'll quantify how well it works in the following slides. And then eventually if you have the spectrum, like in the just calculating currents in CopterCurrents, we also just keep the part or integrate over the part where linear waves are expected. I mean, you can use the full wave number frequency spectrum as you like, of course. But one way to use it is to just take the expected linear part by integrating over a small shell around the dispersion relation. Okay, and we actually take this one step further, because even with this, you can have some non-realistic large values if the residual is small. If the residual is small, if this one is larger, then you can still have large values. So we cap it. We do the same thing, but we have this function m, which is equal to the residual, unless the residual is too small. If it's smaller than some value, this value, then we cap it. And we choose this value without getting into the details. We just choose the value 0.2, such that the full width half max of the spread, of the directional spread of the waves, is 55 degrees. And that's sensible because it's sort of a typical value in wind waves based on the literature. So it's a fair thing to do, I think. Okay. And I just want to show that this residual term is important. So this is on each point here is a different observation with this code. So either a different day or a different time of observation of waves in this manner. And the x-axis is the R squared of the plane fit of the brightness. So basically how good is the linear approximation for the brightness between 0 and 1. And the y-axis is the ratio of the residual to the actual sort of plane fit. And it should be small if it's close to a plane. Sometimes it is, and then you get R square of 1. But in other cases, the residual can be very large, up to 100. So obviously you cannot neglect it. It plays a large role here. So if this is a bad functional form, you will see that this should fail miserably, or vice versa. In any case, in some cases it has a strong effect. So and it varies here by 3 orders of magnitude almost. So again, if we get this wrong, we should probably be able to see it. And then we do this over. So this is an example of applying just CopterCurrents, just the current part, I mean. At one of the C trials, which I'll show you. So this is currents. The magnitude is about 15 centimeters per second, 20 centimeters per second. And there's some validation from a drifter, which is the red part here. In any case, in each one of these, we can also derive the spectrum, and then we can average all the spectra to reduce the uncertainty or the variance. And we do it, we do a conditional average on the R square value of the plane fit, so that in hope of working with the method is more justified from first principles. And that's what we use. Okay, now for field trials or tests, we have done this now in more cases, but in a paper which came out last year, we've shown in 4 different environments. So from bathymetry, from really coastal 15 meters depth to different months, to the shelf 125 meter depth, to the shelf break area 509 meters depth. This is all offshore of Israel. And the conditions, the wave conditions from reference platforms and so on, you can see it wasn't crazy waves, either weak or moderate maybe. You can see the range of typical parameters, peak period of the waves, direction, and so on. Wind speed, the winds weren't very high. These are the drones we use and formats and field of views and the altitude they flew at, just for reference. So this is the first one I'll show you that's the same one as here in this slide. And we didn't have, in that case, a reference wave measurement right there. There was a wave buoy. So this was about 10 kilometers offshore, and there was a wave buoy a few kilometers away. And so this is comparison with that. And we have significant wave height, period, and direction. The reference value from the buoy, which was nearby, is written in text, so significant wave height 47 centimeters. And the difference, and we have reanalysis also values in the gray, and the buoy is in blue, and this is the difference, and a few percent difference. And the period difference was about 20%. Directional difference was 15%. Now, here is from one of the coastal measurements. So in this case, we had an ADCP in the water, which measured the waves from Yaron's group. And you see here a few things. You see the power spectral density of the system is high, and it's hard to make a lot of this, but then you can reduce it to the wave number magnitude spectrum. And in comparison, in blue is from the ADCP, and sorry, in blue, and in black is from the drone. And you see a pretty good fit. And obviously it goes to smaller scales. And I have two more curves here. So the dotted line is just taking the optical spectrum without doing the transformation we did to derive the Stesser's height spectrum. So taking the optical spectrum just obviously it has different units, so just normalizing it so it's the same on this point, which we chose arbitrarily, and you see it has a completely different spectral shape and magnitudes. And the dashed line is the same, but only keeping the linear part of the spectrum around the dispersion curve, so still not doing the job. So obviously the transformation did a major change. This is comparing the bulk metrics, so the sea surface height, period, direction, also directional spread. You see the differences, mostly not too large. This is the same location, but a month, actually this was the second month, so this is a month before, doesn't matter. You still see pretty good comparison. Looks like there was bigger difference, the smallest wave numbers. But anyway, the values were within 20-30%, a bit higher in this case. But the significant wave height wasn't too large, 0.5 meter. So I guess it's easy to get it wrong, 15 centimeter difference. Okay, this is an offshore experiment where we flew from a research vessel. This was, I think, about 50 kilometers offshore above the shelf break, and two different movies at two different heights, I believe. Anyway, it's different hours that this was taken at, so slightly different sea conditions. You see, in this case, the reference platform for the waves was so far spotter buoy, and which was right next which was in the same area, through the plot as well. And you see pretty good comparison as well in the wave number spectra, and again just the optical spectra are completely off. There is less of an agreement in the higher frequencies, but I'm not sure that the small wave the wave buoy does well on the high frequencies itself. These are the bulk metrics. Again, pretty good comparison. In this case, up to like 5-8%. Here, slightly higher. Yeah. Anyway, that's all I had, and I'll skip the summary, and I'll thank my colleagues again. And if there's any questions, we have to take that.
All right, excellent. Thank you so much. So I see a couple questions in the chat, but if I'll give the floor to anyone who wants to just unmute now, go ahead and ask a question. And Misha is still here, so feel free to ask him a question as well. And if no one wants to jump in, go ahead.
No, I think if no one else wants to, then I can reply to these questions in the chat that I see here. I think they're quick.
Yeah, go ahead. And if you don't mind, just read the question as well, so we have it on the recording.
Okay. So there was a question about some bright spots that are visible in the imagery, whether they are targets to match the geolocation by Alice or Alice. And I'm not sure which bright spots you're referring to, but I think they were most likely the white drifters that we dropped. And I think in many of the videos that we collected, they are at some point drifting through the thing. So they have a GPS, of course, but we don't use it for georeferencing. These drones, I think they do a really nice job in keeping their position and giving you an accent, at least in the accuracy we have, which is basically the next question. So I go over to that maybe, which is by Chinchi Shen, who asked about the spatial resolution of the current estimates and whether this is related to the dominant wavelength. Yes, it's height dependent and wave dependent, I think. But since we are quite free in choosing the range of waves that we're looking at, as soon as you have wind, then you also have short waves. So the more you go towards the short waves, the smaller you can make your window. And we are using mostly like 10 meters, I think, delta between the currents, sometimes with some overlap, but it's about 10 meters, I would say, the spatial resolution. And the second part is about the motion of the drone. If we correct for how do you correct the motion of the platforms, drones or radar? We don't. We try to keep the drone stable and let the drone do the job. And the drone is better than us. You can move the drone also with the radar. I mean, if you have a radar on a vessel, or if your drone is moving, then you just include an additional Doppler shift, right? With the radar, it's also the fact that the spatial resolution is so small, so the motion of the radar itself, of the antenna, is not big enough mostly to induce motions that are large enough to induce another Doppler shift. But for the platform motion, that's possible to subtract in post-processing, which we don't do for CopterCurrents mostly. Yep. There's another question, but I'm not sure if it's addressed to me.
Yeah, so I'll just read that question out loud from El Sun, and the question is about LiDAR solutions on drones, direct 3D mapping from LiDAR. I'm not sure. I haven't seen that. I know that I'm at the Field Research Facility in Duck, North Carolina, and we have done line scan LiDAR from drones, for sure. I don't know about 3D point clouds, so if anybody wants to jump in and knows more, please go ahead.
I think I remember a paper by, was it Falk Feddersen and co-authors? I think they did something similar, but I'm not a LiDAR expert, not at all.
I remember, I think I saw publications where people did do that, and very nicely, I think, as I remember. But obviously, it's you need a bigger drone, you need an expensive LiDAR system. Maybe some of them are cheaper, but yeah.
Yeah.
No, yeah.
I mean, for the waves, I think LiDAR. I'm not sure. I mean, if you can, I mean, your accuracy seems to be quite cool. I'm not sure for the waves. I mean, for the currents, I'm quite sure that I mean, you need a clear wave signal because, I mean, that's the funny thing, right? Because the amplitudes, they don't matter a lot. I mean, in the linear dispersion relation, they don't matter at all. So what you need is a clear wave signal, and the better your signal is, the better you see the waves traveling and propagating in space and time, the better your drone fit will be. So I'm quite sure that LiDAR would not help for the drone. Nathan is here. You can you can say something about the polarimetry, maybe.
Yeah, both talks were awesome and really well integrated, I thought. And my intuition is that imaging, I'm biased, of course, but imaging is probably better for this sort of airborne application. I think the sparseness of the LiDAR makes you really, really, really dependent on an excellent motion solution. So you could have a military grade INS, and you still might have decimeter, meter scale errors in your ground sample distance from the LiDARs. I mean, Falk Fedderson's paper was quite impressive. But he was still only getting the first 5 Fourier moments. So he wasn't getting like a true surface mapping point cloud. He was getting, a sort of spatial average of sea surface elevation and tilt. So different application, I guess. I was going to ask Aviv if there's a preprint or a manuscript that was in the works, because I'd really like to keep an eye on this.
Oh, thanks, Nathan. Good to see you. And it's published. It came out last year. Yeah.
Oh, wonderful. Okay. I need to do better literature review then. Thank you.
Yeah, I can send it to you if you like, obviously.
All right, everyone. Thanks for the discussion. I think we'll wrap it up there. Of course, if anyone wants to follow up, with the individual presenters, please feel free to do so. And thanks everyone for coming, and we'll see you at the next one.
Thank you. Bye-bye.
Thanks. Bye.
Thank you. Bye.